Hello everyone, my name is Miranda Pickett and welcome to my Advanced Concepts presentation for Module 1. I am at work, like usual, so please forgive the bad lighting as I'm sitting in my bunk room and it's also almost midnight, so I'm trying to keep my voice a little bit low. But hopefully you'll be able to hear me, and let's get started. So for this Advanced Concepts presentation, we're going to be discussing the Leucine Zipper. And I've put a picture here on the slide just to kind of give an overview of what we're going to be talking about. I find that it helps to be able to visualize images in our head of the things that we're discussing, because it can definitely help us learn a little bit better. So the topics we're going to be discussing in this presentation, to begin with, we're going to be talking about maintaining structure. We're going to be talking about start to finish, all the way from amino acids to quaternary structure. And then we're also going to discuss the key factors or principles that occur in order to allow basically the alpha helices to stay together. But in general, in order for the alpha helices to stay together, we have to talk about the entire zipper staying together. We're also going to be talking about alternate residues, meaning that we're going to be talking about an alternate residue that could replace leucine and keep the hydrophobic core. And we're also going to be talking about an alternate residue that could replace leucine and destabilize the hydrophobic core. And lastly, we're going to be talking about a similar pair of amino acids to that of glutamate and lysine that are involved in the electrostatic interactions in the tertiary structure of the leucine zipper. So let's get started with maintaining structure. I think when talking about maintaining structure for really any protein, it's really important to talk about maintaining the structure from start to finish. It's obviously going to begin with amino acids and end with quaternary structure. However, the amino acids involved in each individual protein and the quaternary structure in each individual protein are going to be different. So in order to really discuss what happens in the leucine zipper, I think it's important that we start from amino acids and end with quaternary structure. So that's what we're going to do. From the start to the finish. And over here, I have included, let me see if I can move my camera here so maybe you can see a little bit better. I have included a picture of two alpha helices that are connected by these leucine residues. So we're going to start with amino acids, and I want you to kind of draw your attention over here to this picture, because when we think about the amino acids involved in the leucine zipper, we want to make sure that we remember that they're the building blocks of proteins. Their amino acids are composed of an alpha carbon amino group, a carboxyl group, a hydrogen ion, and a side chain. The side chain is the part of the amino acid that's going to be variable between amino acids. And particularly with the leucine zipper, we're going to be talking about the amino acids leucine, glutamate, and lysine. Moving on to primary structure, we're talking about the amino acids forming sequences, and in order to form sequences, they need peptide bonds in between the amino acids in the chain. The peptide bond really refers to the amino group of one amino acid binding to the carboxyl group of another amino acid, and in the process it removes a water molecule, and that's when we get a peptide bond. Particularly with the leucine zipper, a leucine residue is in every 7th position along the chain, and this is called a heptad repeat. Already with the primary structure, amino acids forming the chains, they are starting to influence the shape of the beginning of the alpha helices. Moving on to secondary structure, the hydrogen binding between amino groups is really what starts causing the patterns of folding in the proteins, and this is when we actually get our alpha helices. We're actually going to get 2 alpha helices, and in doing this, we're going to be moving on to the tertiary structure. 2 alpha helices gives us a polypeptide formation. Essentially, we'll have 2 peptides, so we'll have a multi peptides. This is where the electrostatic interactions really come into place here. The electrostatic interactions are going to be forming salt bridges, and they do this because glutamate and lysine are opposites. One is acidic, one is basic. And being that they are opposites, like the usual saying goes, opposites attract. So differences in the charges between the amino acids actually cause them to attract to each other, pulling together, and doing this is extremely important for the dimerization specificity. I have such a hard time saying that word. Okay, so now we can move on to the quaternary structure, and this is really the final stage of the protein kind of pulling itself together in the zipper formation. So, in order to be the final stage, basically the folding proteins are becoming stabilized, and they do this via hydrophobic, nonpolar bonding. And they can do this because leucine has hydrophobic side chains that allow this to happen. And quite often, hydrophobic side chain amino acids usually use a bond called a von der Waals bond. It's weak. However, whenever you have multiple collections and they're close together, it makes for a strong overall structure. And with all of the leucine residues forming our von der Waals bonds, we now form a interhelical hydrophobic core, and this is one of the main factors in making sure that this structure is stable. So the key principles of structure maintenance, starting from amino acids, the primary structure are the peptide bonds, the leucine residues, and the heptide repeat. Those all play crucial roles in making sure that the alpha helices stay together. Secondly, with secondary structure, hydrogen bonding is extremely important because it's what creates the alpha helices to begin with. Without having strong alpha helices, you won't have a structure that is able to even be bonded together. Two peptides bonding together won't happen if you don't have strong peptides to make that work. For the tertiary structure, the electrostatic interactions are very important to the structure maintenance. Specifically the dimerization. And lastly, for the quaternary structure, the interhelical hydrophobic core is the most important part of the quaternary structure, involving keeping the alpha helices together. So as I was saying earlier, and as you can see now, it's really not just about the alpha helices sticking together. There's an important part of structure maintenance in every step creating this protein. We're also going to be talking about alternate residues. So in order to keep the core, valine would be the most logical residue to replace leucine in order to keep the hydrophobic core of the zipper. This is because the main difference between valine and leucine is that leucine has an extra methylene group compared to valine. Other than that, they both have hydrophobic side chains, and they're both commonly found on the inside of folded proteins. So in reality, they're almost the same, so I think it would do the best. In terms of destabilizing the core, I think that alanine would be the most reasonable residue to suggest a disrupt in the hydrophobic core, despite it being a hydrophobic side chain amino acid. This is because alanine is a lot smaller than valine or leucine. Therefore, it's likely going to create gaps. And I actually found a study about this. It was done through the University of Alberta, and I'm including the link in the reference page at the end of this PowerPoint. They basically support this reasoning on saying that there will be gaps in the structure. And if it's not a solid structure and there's gaps, it's not going to be as strong. It's going to be destabilized. And it's definitely not going to keep its core. Finding a similar pair. So the key to finding two similar amino acids residues that can interact via electrostatic interaction like glutamate and lysine do is to find two amino acid residues whose side chains are oppositely charged in relation to acidic versus basic. Since we've already used glutamate and lysine, there's only two other options. So in replacement of glutamate, we'd use aspartate because it's negative and acidic, and in replacement of lysine, we would use arginine because it's positive and basic. And using these two pairs, we could, in theory, create another electrostatic interaction. So in conclusion, we have talked about maintaining the structure from start to finish and the key factors involved in maintaining the structure of a leucine zipper. We've also talked about alternate residues in relation to replacing leucine to keep the structure of the hydrophobic core and replacing leucine to destabilize the structure of the hydrophobic core. And lastly, we talked about a similar pair of amino acid residues that could be related to either to both glutamate and lysine. And we found out that opposites attract, and we want a basic versus an acidic amino acid residue. Thank you for listening. Have a great day. And if you want to see my references, they're on the next slide. Here you go. And if you have any further questions, just ask me on the discussion board. Again, thank you for listening. Have a great night.